In the earlier classes, you learnt that the temperature of a body is defined as its degree of coldness or hotness. We feel a body cold or hot because the temperature of the cold body is less than that of our body, and the temperature of a hot body is more than that of our body respectively. But this definition does not help us when it comes to measuring temperature. Let's conduct an experiment to understand this concept better. When a hot iron ball is dropped into a trough containing cold water, we observe the temperature of cold water increasing. Before we continue, let us define heat. Heat is defined as a form of energy that flows from a hot body to a cold body when they are in thermal contact. Heat is an energy that is in transit. Here, the heat flows from the iron ball to the cold water. When we touch a cold body, heat flows from our body to the cold body. If a hot body is touched, heat flows from the hot body to us. Coming back to the experiment, after a sufficient time, it is observed that the temperatures of the iron ball and cold water are the same. Now we say that both the bodies are in thermal equilibrium. When two bodies are in thermal equilibrium, there will be no net exchange of heat energy between them. For example, when a cup with hot tea is placed on a table, heat flows from the cup to surroundings until thermal equilibrium with the surroundings is attained. We define the temperature as a physical quantity that is same for two bodies which are in thermal equilibrium. That means when the teacup is in thermal equilibrium with the surroundings, it is at the same temperature as that of its surroundings. In SI system, heat is measured in joules and temperature is measured in Kelvin. We use a thermometer to measure the temperature of a body. While constructing a thermometer, we need to identify a specific property of a substance that varies linearly with the temperature. In case of a liquid thermometer, the length of the mercury column changes linearly with the change in temperature. Pressure of the gas in a constant volume gas thermometer and resistance of a platinum wire used in resistance thermometer changes linearly with the change in temperature. The temperature of a body can be written as a function of the selected property, say R. To assign a numerical temperature value to a particular length of mercury column in a mercury thermometer, we choose two reference points and assign arbitrary values to them. Among the two reference temperatures, one is considered the lower fixed point, LFP, at T1, which is the freezing point of water or ice point, and the other one is the upper fixed point, UFP, at T2, which is the boiling point of water or steam point. These two reference points used in many standard scales. In the Celsius scale, freezing and boiling points of water are taken as 0 degrees Celsius and 100 degrees Celsius respectively. In the Fahrenheit scale, they are taken as 32 degrees Fahrenheit and 212 degrees Fahrenheit respectively. If R1 and R2 are the values of the identified property, at the two reference temperatures T1 and T2, then temperature T when the property has a value of R is given by T equals to R minus R1 by R2 minus R1 into T2 minus T1. For a Celsius mercury thermometer, if the lengths of the mercury columns are L0 and L100, corresponding to two reference temperatures, T1 is equal to 0 degrees Celsius and T2 is equal to 100 degrees Celsius. Then the temperature T corresponding to a length of L is T is equal to L minus L0 by L100 minus L0 into 100. For any temperature scale, the ratio T minus T1 by T2 minus T1 is constant. This can be used to find relationships among different temperature scales. The relation between Celsius scale and Fahrenheit scales of temperature can be as shown. The same relation can be extended to find the corrected temperature shown by a thermometer which is calibrated incorrectly. If L dash is equal to LFP on a faulty thermometer, U dash is equal to UFP on a faulty thermometer, T dash is equal to temperature of the body read by the faulty thermometer, and L is equal to LFP on an accurate thermometer, U is equal to UFP on an accurate thermometer, T is equal to temperature of the body read by an accurate thermometer. Then the correct temperature of the body is found using the expression. Let's solve a problem based on this formula. The LFP and UFP of a faulty thermometer are minus 5 degrees Celsius and 110 degrees Celsius respectively. If the temperature of a body measured using this faulty thermometer is 45 degrees Celsius, then what is the correct temperature of the body? Here, T is equal to T degrees Celsius, L is equal to 0 degrees Celsius, U is equal to 100 degrees Celsius, T dash is equal to 45 degrees Celsius, L dash is equal to minus 5 degrees Celsius, U dash is equal to 110 degrees Celsius. Upon substituting the values in the equations and solving, we find that the actual temperature is 43.5 degrees Celsius. When a mercury thermometer and an alcohol thermometer are used to find the temperature of a substance, they may not show the same temperature readings. This is because the thermal properties of different substances are different, and the rate of expansion of a substance changes with temperature. That means the per degree expansion of a liquid is not uniform at all temperatures. The readings shown by different thermometers may coincide at calibration points, but may vary at other temperatures. Due to this, these thermometers are of no use when accurate measurement of temperature is needed. It is experimentally observed that the temperature readings of gas thermometers are independent of the gas used. Hence, these are more reliable for the accurate measurement of temperature. A gas thermometer works on the basis of variation in the pressure or volume with the temperature of the gas in it. Boyle's law states that if the temperature of a given mass of gas is constant, then its pressure is inversely proportional to its volume. At constant temperature T, PV is equal to constant, where P is the pressure of the gas and V is the volume of the gas. According to Charles' law, at constant pressure, the volume of a given mass of gas is directly proportional to its temperature T. Therefore, V by T is constant. On combining equations 1 and 2, we get PV by T is equal to constant. This is known as ideal gas law. PV is equal to mu RT is a generalized ideal gas equation, where mu is the number of moles of gas and R is 8.31 joule per mole per Kelvin, which is the universal gas constant. The constant volume gas thermometer works on the principle of the ideal gas law. Since PV is directly proportional to T, when the volume of a given sample of gas is constant, its pressure changes linearly with the temperature of the gas. When a graph is plotted between pressure and temperature, a straight line is obtained. If the density of the gas is low, the graph will be a perfect straight line for all gases over a large temperature range. Let's look at the pressure-temperature graph for different gases at low density. When extended towards negative temperatures, all these straight lines meet at a point represented by the temperature minus 273.15 degrees centigrade. That means, at temperature minus 273.15 degrees centigrade, if the gas is still in the same state, its pressure reduces to zero. In fact, at this temperature, the average kinetic energy of gas molecules becomes zero. As a result, they cease to move and settle at the bottom of the container, and the pressure exerted by them reduces to zero. A new temperature scale was developed by Lord Kelvin by designating this temperature of minus 273.15 degrees centigrade as zero. This new temperature scale is known as the Kelvin or absolute temperature scale. The zero of this scale is called absolute zero. The temperature of a body on the absolute scale is expressed in Kelvin and is called absolute temperature and is represented by the letter T. The size of a degree on the Kelvin scale is identical to the size of a degree on the Celsius scale. For example, if the temperature of a body is increased by 1 degree centigrade, then the corresponding change on the absolute scale is 1 Kelvin. The relation between the absolute temperature and Celsius temperature is expressed as T and is equal to Tc plus 273.15. Here is a comparison between the Kelvin, Celsius and the Fahrenheit temperature scales. Many substances expand on heating and contract on cooling. An increase in the dimensions of a body due to an increase in its temperature is called thermal expansion. For example, the volume of the mercury in a mercury thermometer changes with a change in its temperature. Let's look at some examples of thermal expansion of substances that we come across in daily life. Rails are produced in fixed lengths, and fish plates are used to join them. The gaps provided between rails allow them to expand during summer. Expansion joints are provided while constructing bridges. When the temperature of any metallic body is increased, its length, surface area, and volume may increase. Expansion along length is defined as linear expansion. Expansion of the surface area of a solid is called areal expansion, and expansion of its volume is called volume expansion or cubical expansion. Let us consider a thin metal rod of length L at a temperature T. It is experimentally observed that the change in the length of the rod, delta L, is directly proportional to the change in its temperature, delta T, and also directly proportional to the initial length of the rod. Thus, we get equations 1 and 2. Combining equations 1 and 2, we get the expression delta L equal to the product of alpha L, L delta T, where alpha L is the proportionality constant called coefficient of linear expansion and is characteristic of the material of the rod. The fractional change in length delta L by L is equal to alpha L into delta T. Similarly, the fractional change in the area is experimentally found to be directly proportional to the change in the temperature. That is, delta A by A is equal to alpha A into delta T. That is, the fractional change in the area, delta A by A, is equal to alpha A into delta T, where alpha A is the coefficient of areal expansion. If the volume of a solid body is V and delta V is the change in volume for a change of temperature delta T, then delta V is equal to alpha V into delta T, where alpha V is called the coefficient of volume expansion. Though the coefficient of expansion is a characteristic of the substance, its value depends on its temperature. For many solids, expansion is analogous to photographic enlargement. For example, if a metallic sheet with identical holes, as shown, is heated, then the expansion is proportionate in all directions. The length and breadth of the sheet, radii of all the holes, and the distance between two holes all increase proportionately. Substances that expand at the same rate in all directions are called isotropic substances. For a perfect isotropic material, the coefficients of thermal expansion are related as alpha V equals to 3 alpha L and alpha A equals to 2 alpha L. Let's prove the identity by considering a cube of length L naught. Its total surface area A naught equal to 6 L naught square and its volume V naught equal to L naught cube. When the temperature of the cube is increased by delta T, let the length of each side be increased by delta L. Therefore, the length of the side after expansion L equals to L naught plus delta L. Change in area delta A equals to 6 into L naught plus delta L whole square minus 6L naught square. This is equal to 6 into delta L square plus 2L naught delta L. The term delta L square can be ignored as the value is negligible. Then we get delta A is equal to 6 into 2L naught delta L. Now, by dividing delta A by A naught, we get 6 into 2L naught delta L by 6L naught square. On further simplification, we get alpha A equals to 2 alpha L. Let this be equation 1. Change in volume delta V equals to L naught plus delta L whole cube minus L naught cube. This is equal to L naught cube plus 3L naught square delta L plus 3L naught delta L square plus delta L cube minus L naught cube. The terms delta L square and delta L cube can be ignored as their values are negligible. Then we get delta V is equal to 3 into L naught square into delta L. Now by dividing delta V by V naught, we get 3 into L naught square delta L by L naught cube. On further simplifying, we get alpha V equals to 3 alpha L. Let this be equation 2. Let us now look at the expansion of solids at an atomic level. In a solid, the atoms are arranged in fixed positions. Expansion of a solid indicates that the average separation between the atoms is increased. As the temperature increases, the atoms vibrate with more vibrational energy, and the amplitude of vibrations also increase. The graph shown is the potential energy curve for two adjacent atoms in a solid as a function of their internuclear separation. Since the potential energy curve is an asymmetric curve, the average separation between atoms increases as temperature increases. As liquids do not have a specific shape, they do not have linear and aerial expansion as solids do. They have expansion in volume only. When a liquid in a container is heated, both the liquid and the container expand. Hence, for liquids, we have two categories of expansions, namely real and apparent. The apparent expansion of a liquid is the expansion that appears. The apparent expansion of the liquid is equal to the real expansion of the liquid minus expansion of the container. Unlike other liquids, water exhibits irregular expansion between 0 degrees centigrade and 4 degrees centigrade. If the temperature of water is raised from 0 degrees centigrade to 4 degrees centigrade, instead of expanding, it actually contracts. This means a given mass of water occupies least volume and, as a consequence, will have maximum density at 4 degrees centigrade. This anomalous expansion of water enables aquatic animals and plants to survive in water. Lakes and ponds freeze first on the upper surface of water. The frozen water body, which is the ice, floats on the denser water. When a solid, liquid and a gas are heated, the gas expands more than the solid and the liquid. For ideal gas, PV is equal to mu RT. Let this be equation 1. If the pressure of the gas is constant, on differentiating equation 1, we get P delta V equals to mu R delta T. Let this be equation 2. On dividing equation 2 by equation 1, we get delta V by V is equal to delta T by T. But delta V by V is equal to alpha V into delta T. Hence, for an ideal gas, alpha V is equal to 1 by T. For gases, the coefficient of volume expansion is inversely proportional to the absolute temperature of the gas. Let us now discuss thermal stress. Consider a rod rigidly fixed at both ends to prevent expansion. If the temperature of the rod is changed, then the stress that develops in the rod is called thermal stress. The stress developed in a body when not allowing it to expand while heating is called thermal stress. If the length of the rod is L and delta L is the change in its length for a temperature change of delta T, then delta L by L is equal to alpha L into delta T. Let this be equation 3. If the rod is rigidly fixed, then thermal stress is expressed as F by A, which is equal to Y into delta L by L, where Y is Young's modulus of the material. Let this be equation 4. From equations 3 and 4, thermal stress is expressed as Y into alpha L into delta T. The force F acting on the rod must be equal to the product of Y, A, alpha L and delta T. You have already learned that if there is no change in the state of a body, its temperature increases when it absorbs heat energy from the surroundings and decreases when it emits heat energy. Now let us study the factors that influence the heat required to change the temperature of a body. Consider a given quantity of water being heated using a source that supplies heat at the rate of 100 joules per second. If the initial temperature of water is 303 Kelvin and the temperature is increased to 308 Kelvin at the end of 3.5 minutes and to 313 Kelvin at the end of 7 minutes, the amount of heat absorbed for a rise in temperature of 10 Kelvin is double the amount of heat absorbed for a rise in temperature of 5 Kelvin. This means the quantity of heat absorbed or emitted, delta Q, by a body is directly proportional to its change in temperature, delta T. Let this be equation 1. Heat capacity denoted by S of a body is defined as the heat absorbed or emitted per unit change in its temperature. Therefore, S is equal to delta Q by delta T. The SI unit of heat capacity is joules per Kelvin. In the experiment shown earlier, heat absorbed by the given quantity of water in 7 minutes can be expressed as delta Q equals to RT. Substituting the values of R and T, we get delta Q equals to 42,000 joules. The corresponding rise in temperature, delta T, is 10 Kelvin. Substituting the values of delta Q and delta T, the value of heat capacity S is 4,200 joules per Kelvin. Now let us double the quantity of water. Then the time required to raise the temperature from 303 Kelvin to 308 Kelvin is 7 minutes. This means when the mass of water is doubled, the heat required to raise the temperature by 5 Kelvin is also doubled. Hence, the quantity of heat, delta Q, required to raise the temperature of a body depends on its mass also. Therefore, delta Q is directly proportional to mass m. Let this be equation 2. From equations 1 and 2, we can write that delta Q is directly proportional to m delta T, or delta Q is equal to S m delta T, where S is the specific heat capacity of the substance. Specific heat capacity is the quantity of heat absorbed or emitted by a unit mass of a substance for a change in its temperature by 1 unit. Specific heat capacity S can be expressed as S equals to 1 by m into delta Q by delta T. The SI unit of specific heat capacity is joule per kilogram Kelvin. Specific heat capacity depends on the nature of the substance. Different materials have different specific heat capacity values as shown in the table. The specific heat capacity of water is 4,186 joules per kilogram Kelvin. For practical purposes, we can take the value to be 4,200 joules per kilogram Kelvin. Water is used as a coolant in automobile radiators because of its very high specific heat capacity. The specific heat capacity of a substance also depends on its temperature. Different amounts of heat are required for a unit rise in temperature of a unit mass of a substance at different temperatures. For example, the variation of the specific heat capacity of water with temperature is as shown. This is why a specific temperature range is given in the definition of calorie, which is a general unit of heat. A calorie is defined as the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade. Sometimes, it is more convenient to describe the quantity of a substance in terms of moles, mu, rather than mass, m. When a given substance is expressed in moles, its specific heat capacity is known as molar specific heat capacity and is represented by C. The molar specific heat capacity of a substance is defined as heat capacity per mole of the substance. This is given by C equals to S by mu equals to 1 by mu into delta Q by delta T. The SI unit of molecular specific heat capacity, C, is joules per mole Kelvin. Molar specific heat capacity also depends on the nature and temperature of the substance. The definition of specific heat capacity is applicable for all states of matter, namely solids, liquids, and gases. But for gases, the heat required to raise the temperature depends on the process involved. If we heat a gas by keeping its pressure constant, then the heat delta Q required to raise the temperature of 1 mole of gas by 1 unit is called its molar specific heat capacity at constant pressure and is denoted by Cp. Cp is equal to 1 by mu into delta Q by delta T at constant pressure. The molar specific heat capacity at constant volume, denoted by Cv, is the heat required to raise the temperature of 1 mole of a given gas at a constant volume by 1 unit. Cv is equal to 1 by mu into delta Q by delta T at a constant volume. Let's take 2 iron rods, A and B, at 2 different temperatures and place them in a thermally insulated box and make sure they are in contact with each other. We know that heat energy flows from a hot body to a cold body. Since they are in a thermally insulated box, no heat escapes to the surroundings. Heat energy emitted by the hot body must be completely absorbed by the cold body. Even when more than 2 bodies are placed in a thermally insulated box, some bodies lose heat energy and other bodies gain heat energy. The total heat energy lost by the hot bodies must be completely absorbed by the cold bodies. This means when 2 or more bodies at different temperatures are brought into thermal contact, and if no heat is allowed to escape to the surroundings, then the total heat lost by the hot bodies must be equal to the total heat gained by the cold bodies. This is called the principle of calorimetry. Calorimetry is the science of measuring heat. Heat gained or lost by a body is expressed by the equation delta Q equals the product of M, S and delta T, where M is the mass of the body, S is the specific heat capacity of the body, and delta T is the change in temperature of the body. For example, an apple of mass 0.2 kilograms and specific heat capacity of 3640 joules per kilogram per Kelvin is placed in a refrigerator. If its temperature is changed from 30 degrees Celsius to 10 degrees Celsius, find the heat that flows out of the apple. Given that mass M equals to 0.2 kilograms, specific heat capacity S is equal to 3640 joules per kilogram per Kelvin. Change in temperature delta T is equal to 30 minus 10, which is equal to 20 degrees Celsius. Heat that flows out delta Q is equal to the product of M, S and delta T. Substituting these values and calculating, we get delta Q equal to 14,560 joules. In calorimetry experiments, a device known as a calorimeter is usually used to make heat measurements. A calorimeter consists of a small metallic vessel with a stirrer, and usually both are made of copper. The vessel is placed in a wooden box with insulating material surrounding the copper vessel in the box. This wooden box acts as a heat shield and reduces heat loss. There is a wooden lid on the top of the box, where there is a provision to place a thermometer and also to pass the stirrer through. Let us find the specific heat capacity of a solid using the principle of calorimetry. To do this, a Reynolds apparatus and a calorimeter are used. As we use water in the calorimeter, we need to take a solid that is denser than water and insoluble in water, say a metal ball. First, the calorimeter with stirrer is weighed using a physical balance. Let its mass be m1. We now weigh the material used in the activity, that is, the metal ball. Let its mass be m2. Pour sufficient water into the calorimeter, and then the mass of the calorimeter and water is found to be m3. Then mass of the water is equal to m3 minus m1. Note the temperature of the water. Let it be T1. Now, heat the metal ball in the steam chamber of Reynolds apparatus till the thermometer in the apparatus shows a steady reading for a few minutes. And let the temperature of the metal ball be T2. The wooden partition separating the steam chamber and the calorimeter provides thermal insulation to the calorimeter from the chamber, so that there is no transfer of heat from the chamber to the calorimeter. Now bring the calorimeter below the sliding base of the steam chamber and slide open the base of the chamber. Drop the metal ball into the water in the calorimeter and stir the mixture for some time. Then note the equilibrium temperature T3. Let the specific heat capacity of the copper metal ball and water be S1, S2 and S3 respectively. Here, heat is lost by the hot metal ball and gained by the cold calorimeter and water. Heat lost by the metal ball is equal to M2 into S2 into T2 minus T3. Heat gained by the calorimeter is equal to M1 into S1 into T3 minus T1. Heat gained by the water is equal to M3 minus M1 into S3 into T3 minus T1. Applying the principle of calorimetry, heat lost by a hot body is equal to the heat gained by a cold body, which is expressed as M2 into S2 into T2 minus T3 equals M1 into S1 into T3 minus T1 plus M3 minus M1 into S3 into T3 minus T1. On further simplifying, S2 equals M1 into S1 into T3 minus T1 plus M3 minus M1 into S3 into T3 minus T1 by M2 into T2 minus T3. Matter exists in three states: solids, liquids, and gases. The transition of matter from one state to another is called change of state. The change of state from solid to liquid is called melting. And from liquid to solid, it is called fusion. A change of state from liquid to gas is called boiling or vaporization. And from gas to liquid is called condensation. Consider a round-bottomed flask with a thermometer and steam outlet fixed through the cork. Place some ice cubes at minus 10 degrees centigrade in the flask and start heating. Now, let us observe the change in the temperature of the contents and plot a graph between temperature along the y-axis and time along the x-axis, as it is an independent quantity. Initially, we observe a rise in the temperature of the ice as it absorbs heat energy. This continues till the ice attains a temperature of 0 degrees Celsius. If we continue heating the flask, strangely, we don't observe any rise in the temperature in the ice cubes. But we can observe some of the ice cubes melting. This indicates the change of state of ice to water. And during this process, both solid ice and liquid water coexist. No change in the temperature is observed till the entire ice in the flask melts to water. That means, on absorbing heat, ice at 0 degrees Celsius converts to water at 0 degrees Celsius. The temperature at which the solid and liquid states of a substance are in thermal equilibrium with each other is called melting point. Thus, the melting point of ice is 0 degrees Celsius. In this case, the heat supplied is utilized to increase the internal energy of the substance. The amount of heat absorbed by a unit mass of a substance to convert it completely from one state to another state is called latent heat, usually denoted by L. The word latent means hidden and is derived from the Latin root word latentum, which means to lie hidden. Latent heat is a characteristic of the substance. If Q is the heat required to convert a substance of mass m completely from one state to another at a constant temperature, then Q is equal to the product of M and L, where L is the latent heat of the substance for that particular change of state. The latent heat in the case of solid to liquid transition is called latent heat of fusion, denoted by LF. If we continue heating the water in the flask, its temperature starts rising again and continues to rise to 100 degrees Celsius. As the water gets heated, first, the air that is dissolved in water forms small bubbles at the bottom of the container. After some time, steam bubbles form at the bottom of the flask and move upwards. As they reach the cooler water at the top, they condense and disappear. The process of bubbles of steam forming and reaching the surface intensifies, and we say that the water is boiling. At this point, once again we observe no change in the temperature of the water, even though the water changes to water vapor. Even if we continue heating, the temperature of the water remains constant, and the heat absorbed is used to change the state from liquid to gaseous state. The constant temperature at which the liquid and the vapor states of a substance coexist is called boiling point. The heat required to convert 1 unit mass of a substance completely from the liquid to gaseous state at its boiling point is called latent heat of vaporization and is denoted by LV. If the rate of heat supplied by the source is known, a temperature time graph can be converted into a temperature heat graph, which is usually called a heating curve. Some parts of the curve are parallel to the x-axis, and some of them are inclined. The inclined portions of the graph correspond to a particular state of the substance. The slopes of the inclined portions are not equal. This means a substance will have different specific heat capacities in different states. The temperatures corresponding to parallel portions of the graph correspond to melting and boiling points. The melting point and boiling point of a substance depends on pressure. If measured at standard atmospheric pressure, they are called normal melting point and normal boiling point. For example, the melting point of ice decreases with an increase in pressure. If a metallic wire with 2 masses tied to both ends is placed on a slab of ice, we observe it passing through the slab. As the wire exerts pressure, the ice beneath it melts. When the wire passes through, the water above the wire freezes once again. This phenomenon of refreezing is called regulation. In fact, ice skating is possible only because of regulation. When the skaters move on ice, due to the sharp wedges at the bottom of the skates, there is an increase in pressure on the ice, and due to this, the ice beneath melts below its normal melting point. This makes the motion of the skaters smooth and friction-free. The boiling point of water increases with an increase in pressure. To understand this, let us return to the experiment where water was heated in a round-bottomed flask. When the steam outlet is closed, the pressure inside the flask increases, and the boiling point of water also increases. Therefore, the water in the flask stops boiling after some time. After absorbing more heat, the temperature of the water increases to a new boiling point and it starts boiling again. A pressure cooker works on this principle. When food is cooked in a pressure cooker, the pressure that builds in the cooker increases the boiling point of water to higher than normal. And the food in the cooker is cooked at a higher temperature than if it were cooked outside. This makes cooking quicker and cost-effective. Cooking is difficult in hill stations because at high altitudes, the atmospheric pressure is lower than normal. And as a result, the boiling point of water decreases. Usually, on heating, substances change from solid to liquid and then from liquid to gaseous state. There are certain substances which change from the solid to gaseous state directly. This phenomenon of changing directly from the solid to gaseous state is called sublimation. Dry ice and iodine are some examples of such substances. Transfer of heat takes place in three different modes. They are thermal conduction, convection, and radiation. First, let us learn about thermal conduction. Thermal conduction is a mechanism of heat transfer between two adjacent parts of a body, or between two bodies in thermal contact because of a temperature difference. For example, observe the person holding an iron rod at one end and placing the other end in fire. One end of the iron rod, which is in the flame, at a high temperature and the other end at low temperature. Heat flows from the hot end to the cold end by thermal conduction. And as a result, after some time the person drops the rod. When heat is supplied at one end of the rod, the molecules in hotter regions gain kinetic energy and start vibrating faster. These vibrations are passed on to neighboring molecules through intermolecular bonds. In this way, the energy is eventually transferred to the whole body. Thermal conductivity of a substance, which is usually referred to as conductivity, depends on the state and nature of a substance. In solids, metals are very good conductors of heat. This is due to two reasons. One is that the molecules are very closely packed and thus help transfer vibrational energy quickly. The second reason is that metals contain a large number of free electrons, which also contribute to the quick transfer of heat energy. The free electrons close to the heat source receive heat and move faster through the metal. During this process, they collide with molecules and other electrons and pass a part of their energy on to them. In the case of gases, the molecules are far apart and hence the exchange of energy among them is very difficult. Therefore, gases are very bad conductors of heat. In the case of liquids, the intermolecular space is more than in solids and less than in gases. Therefore, the conductivity of liquids is greater than that of gases, but less than that of solids. Now consider a metallic rod of length L and a cross-sectional area A. Let the two ends of the rod be maintained at two different constant temperatures, T1 and T2. These temperatures are maintained by placing one end of the rod in a steam chamber and the other in a chamber with flowing water. Temperatures T1 and T2 are maintained in such a way that T1 is greater than T2. The end of the rod where the temperature is T1 is hotter than the other. Let us also assume that the rod is fully insulated and there is no loss of heat to the surroundings. Heat starts flowing from the hot end to the cold end. And after some time, there will be a steady flow of heat through the rod. The rate of heat flow is defined as heat current H. If delta Q is the heat flowing across any cross-section in time, delta T, then heat current H is equal to delta Q by delta T. Let this be equation 1. In a steady state, the temperature of the rod decreases uniformly from the hot to the cold end of the rod. The change in temperature per unit length is defined as the temperature gradient. Since the change in temperature for a length of L is T2 minus T1, the temperature gradient is expressed as T2 minus T1 by L. Let this be equation 2. It is experimentally found that in a steady state, heat current H is directly proportional to the temperature difference between the two ends and cross-sectional area of the rod. It is also found that H is inversely proportional to the length of the rod. That is, H is equal to delta Q by delta T, which is equal to Ka into T1 minus T2 by L. Let this be equation 3, where K is the proportionality constant and is called the thermal conductivity of the material. The SI unit of thermal conductivity is joule per second per meter per Kelvin or watt per meter per Kelvin. For a rod, the mathematical expression L by Ka is defined as its thermal resistance R, where L and A are the length and cross-sectional areas of the rod respectively, and K is the thermal conductivity of the material of the rod. Now, equation 3 can be written as heat current H is equal to T1 minus T2 by R. Let this be equation 4. Equation 4 is identical to Ohm's law of current electricity. This identity can be extended to some other cases as well. For example, if two rods of thermal resistances R1 and R2 are connected in series, then the equivalent thermal resistance R of the combination is expressed as R is equal to R1 plus R2. On the other hand, if they are connected parallelly, then the equivalent thermal resistance of the combination R can be found using the relation 1 by R is equal to 1 by R1 plus 1 by R2. Now consider two bars each of length L and a cross-sectional area A. The bars, made of different material of thermal conductivity K1 and K2 respectively, are soldered end to end, and the free ends are maintained at two different temperatures T1 and T2. with T1 greater than T2. In a steady state, heat current in the first rod is equal to heat current in the second rod. If the junction temperature is T0, then K1A into T1 minus T0 by L is equal to K2A into T0 minus T2 by L. Or K1 into T1 minus T0 is equal to K2 into T0 minus T2. The junction temperature T0 is equal to K1 T1 plus K2 T2 by K1 plus K2. Since heat current through the combination is equal to heat current through the first rod, if the equivalent thermal conductivity of the combination of two conductors is K, then we can write Ka into T1 minus T2 by 2L is equal to K1A into T1 minus T0 by L. On simplifying, we get K into T1 minus T2 is equal to 2K1 into T1 minus T0. Substituting the value of T0, we get K into T1 minus T2 is equal to 2K1 into T1 minus K1 T1 plus K2 T2 by K1 plus K2. On further simplifying, we get K into T1 minus T2 is equal to 2K1 into K2 into T1 minus T2 by K1 plus K2. Therefore, K is equal to 2 K1 K2 by K1 plus K2. This is the expression for equivalent conductivity when two conductors are connected in a series. The table shows the thermal conductivities of some materials. Metals have very high thermal conductivities and hence conduct heat rapidly. Materials like wood, bakelite, and wool are bad conductors. When loss of heat by conduction is to be restricted, the body must be surrounded by an insulating substance. For example, we use woolen clothes in winter to prevent loss of heat, as the air is entrapped in the pores of the wool fabric, which acts as an insulator. When heat is to be transmitted faster, good conductors are used in the process. For example, cooking utensils, water coolant systems in car radiators, and nuclear power plants all use good conductors. Let us conduct an experiment to understand what is meant by convection. Take some water in a container and heat it by placing it on a burner. The bottom of the container absorbs heat from the burner and then conducts it into the water. Since the entire water body is not in contact with the bottom of the container, all the layers of water cannot absorb heat by conduction. The water that is in contact with the bottom of the container absorbs heat by conduction, and its temperature increases. Because of a rise in temperature, this part of water expands, and as a result, its density decreases. This low-density warm water is lifted up towards the surface due to buoyancy, and the denser cold water moves down and comes into direct contact with the hot base of the container. Once again, the water in contact with the base of the container becomes hot and is replaced by a colder part of the water in the container. This way, all the water gets heated. Heat transfer by actual motion of matter from one region to another is known as thermal convection. Since convection involves bulk movement of different parts of matter, this mode of heat transfer is possible only in fluids. Thermal convection can be natural or forced. If the convection is caused by difference in density due to thermal expansion, then it is called natural convection. The heating of water is an example of natural convection. Gravity plays an important role in natural convection. That is why, in natural convection, heating is always in the upward direction. If the container is heated at the top, transmission of heat by convection does not take place in the downward direction. Natural convection is responsible for many day-to-day phenomena. For example, in coastal areas, wind blows from the sea to the land in the daytime. This is known as sea breeze. The sea water warms up slower than the land because of high specific heat capacity of water. As a result, the air above the land becomes hotter and moves up, creating a low pressure area. Now, the air above the sea water moves towards the land and forms the sea breeze. During the night time, exactly the reverse process takes place. Air moves from the land to the sea. This is known as land breeze. Trade winds are another example of natural convection. The steady surface winds blowing from the northeast and the southeast towards the equator are called trade winds. The equatorial region receives more heat energy than the polar regions. Air at the equatorial region is much hotter than the air at the polar regions. In the absence of any other effect, the air at the equator rises and moves towards the polar regions and descends at the poles. The cold air from the polar region moves towards the equatorial region, forming convection currents. But because of the Earth's rotation, air at the equatorial region moves with a speed of 1,600 kilometers per hour in the eastward direction, whereas the speed of these winds is almost zero at the poles. These two movements of air, one because of convection and the other because of the Earth's rotation, result in trade winds. In the northern hemisphere, instead of descending at the North Pole, the air descends at 30 degrees north latitude and moves towards the equator. Similarly, in the southern hemisphere, instead of descending at the South Pole, the air descends at 30 degrees south latitude and moves towards the equator. Let us now discuss forced convection. If the movement of matter is caused by a pump or blower for transfer of heat, it is called forced convection. Let us look at some common examples of forced convection systems. One of the most common examples of forced convection that we see around us is the working of a hair dryer. Air at room temperature is sucked by a motor and heated up by forced convection as it passes over the hot coils inside the dryer. This hot air is then blown out through the nozzle provided. The human circulatory system is another example of forced convection. Blood is forced through the circulatory system by the heart to maintain the required uniform temperature throughout the body. The third mode of heat transfer is thermal radiation, where heat is transmitted even through vacuum in the form of electromagnetic waves. The electromagnetic waves emitted by a body by virtue of its temperature is called thermal radiation. Heat energy received from the sun is in the form of radiation. Like any other electromagnetic waves, thermal radiation can travel at a speed of 3 × 10 raised to the power 8 meters per second. In fact, all bodies emit thermal radiation. The rate of emission of thermal radiation depends on the temperature of the body. When thermal radiation falls on a body, it is partly absorbed and partly reflected. The amount of heat absorbed by a body depends on its color. Black bodies have a greater capacity of absorbing radiant energy. This is the reason why we wear light-colored clothes during summers and dark-colored ones during winters. A thermos flask is designed to minimize heat loss by all the 3 modes of heat transfer. This consists of a double-walled evacuated glass vessel with its inner and outer walls coated with silver. The vacuum between the 2 walls prevents heat loss by conduction and convection. The silver coating on the walls prevents exchange of heat by radiation. Therefore, heat transfer is minimized by controlling conduction, convection, and radiation. It is a common phenomenon that a hot body exchanges heat with its surroundings and cools. The heat lost by the body to its surroundings per unit time is called the rate of cooling of the body and depends on several factors. Let's conduct an experiment to study the factors that influence the rate of cooling of a body. Let's take some water at room temperature in a calorimeter and place in it a thermometer. If the temperature of the water is T1 degrees Celsius, then the temperature of the surroundings is also T1 degrees Celsius. Now, let us first heat the water in the calorimeter to raise the temperature to say T2 degrees Celsius. And then stop heating and allow the water in the calorimeter to cool. Start a stop clock and note the temperature T2 of the water at regular intervals, say after every minute. The difference in temperature between the water and its surroundings is expressed as delta T, which is equal to T2 minus T1. Delta T can be computed for each value of T2. When a graph is plotted by taking delta T along the y-axis and time t along the x-axis, we get a curve. The graph indicates that the cooling of water depends on the temperature difference between the water and its surroundings. The greater the temperature difference, the greater the fall in the temperature of the hot water. With the passage of time, the temperature difference between the hot water and its surroundings decreases, and hence the change in the temperature of the water also decreases. Newton made a systematic study of the cooling of different bodies and proposed a law known as Newton's law of cooling that holds good for small differences in temperature between a hot body and its surroundings. Newton's law of cooling states that the rate of heat lost by a body is directly proportional to the difference in temperature between the body and its surroundings. If a body is at a temperature T2 degrees Celsius and its surroundings are a temperature of T1 degrees Celsius, where T2 is greater than T1, then the rate of loss of heat is expressed as minus dQ by dt is proportional to T2 minus T1, or minus dQ by dt is equal to K into T2 minus T1. Let this be equation 1, where K is the proportionality constant, which depends on the area and nature of the body. Let the mass of the body be m, whose specific heat capacity is S, at an initial temperature T2, with its surroundings at a temperature T1. If the temperature of the body is changed by delta T2 because of a small loss of heat delta Q in a small interval of time delta T, then delta Q can be expressed as a product of m, S and delta T2. Then the rate of heat loss is equal to delta Q by delta T equals to ms delta T2 by delta T. Let this be equation 2. But according to Newton's law of cooling, we have minus delta Q by delta T is equal to K into T2 minus T1. Let this be equation 3. Combining equations 2 and 3, we get minus ms into delta T2 by delta T is equal to K into T2 minus T1, or delta T2 by T2 minus T1 is equal to minus K by ms into delta T. Let this be equation 4. Taking limits on both sides, we get dt2 by T2 minus T1 is equal to minus K by ms into dt. On integrating this expression on both sides and simplifying, we get log to the base e T2 minus T1 is equal to minus K by ms into T plus C. Let this be equation 5. This can also be written as T2 minus T1 is equal to e to the power minus K by ms into T plus C, which is equal to e raised to the power C into e raised to the power minus K by ms into T. Let this be equation 6. If we define K equal to K by ms and C equal to e raised to the power C, then equation 6 becomes T2 minus T1 is equal to C into e to the power minus kt, or T2 is equal to T1 plus C into e to the power minus kt. Let this be equation 7. This equation can be used to calculate the time taken for a body to cool through a particular range of temperature. The law is applicable to small temperature differences. Even when the transfer of heat is due to a combined effect of conduction, convection, and radiation, the rate of cooling is proportional to the difference in temperature. For example, if a beaker of hot water placed in surroundings whose temperature is 25 degrees Celsius takes 5 minutes to cool from 75 degrees Celsius to 50 degrees Celsius, how much more time does it take to cool to 30 degrees Celsius? Using Newton's law of cooling, minus delta T2 by delta T is equal to K into T2 minus T1. Therefore, minus delta T2 by T2 minus T1 is equal to K into delta T. Let this be equation 1. This can be written as a change in the temperature by temperature of the body minus temperature of the surroundings is equal to K into time. It is given that the initial temperature of the body is 75 degrees Celsius and its temperature after 5 minutes is 50 degrees Celsius. Since the temperature of the hot body is not constant, the average of the initial and final temperatures has to be calculated to arrive at the value of T2. When the body is cooled from 75 degrees Celsius to 50 degrees Celsius in 5 minutes, the average temperature of the body is the average of 75 degrees Celsius and 50 degrees Celsius, which is equal to 62.5 degrees Celsius. Delta T2 is equal to minus 25 degrees Celsius. Minus delta T2 is equal to 25 degrees Celsius. Delta T is equal to 5 minutes. Substituting these values in equation 1, we get 25 by 62.5 minus 25 is equal to K into 5. On further simplifying, we get K is equal to 5 by 37.5. Now, the values to calculate the time for the water to cool from 50 degrees Celsius to 30 degrees Celsius are the average of 50 degrees Celsius and 30 degrees Celsius is 40 degrees Celsius, and hence T2 is equal to 40 degrees Celsius. T1 is equal to 25 degrees Celsius. Delta T2 is equal to minus 20 degrees Celsius. Minus delta T2 is equal to 20 degrees Celsius. We need to find the value of T. (20 by 40 minus 25 is equal to K into T. On further simplifying, we get T is equal to 4 by 3K. We know that K is equal to 5 by 37.5. Substituting the value of K, and simplifying, we get the value of T equal to 10 minutes. Therefore, it takes 10 minutes for the temperature of the water to fall from 50 degrees Celsius to 30 degrees Celsius. Newton's law of cooling can be verified by conducting the following experiment. A double-walled vessel is filled with water between the walls, and the mouth of the vessel is closed with a cork through which a thermometer is inserted. Let the temperature reading be T1 degrees Celsius. A copper calorimeter with hot water is placed inside the vessel. Close the mouth of the calorimeter with a 2-holed cork. With a stirrer passing through one hole and a thermometer through the other, let the reading in this thermometer be T2 degrees Celsius. The temperature of the hot water in the calorimeter is noted after equal intervals of time. When a graph is plotted with log to the base e, T2 minus T1 along the y-axis and time t along the x-axis, based on the experimental results, we get a straight line with a negative slope.